Okay, I hope you are not all too exhausted and tired out. So today in this class we'll look at some pretty interesting stuff, which is something which forms the backbone of many RF communication system calculations. Okay. So just continuing with our discussion on noise figure. So we looked at both extremes now, right? We looked at one extreme, which is when you have very large signals, you end up with non-linearity. You have distortion, intermodulation, and all those non-linear effects. Then we came to the other extreme, where you don't have much signal. I mean, your signal swing and everything is extremely limited. So you are now basically fighting with noise, right? So that is the kind of that is the range to which we have come now, and we looked at noise figure and other things. So now what we will do is, so we even for noise we looked at noise figure, how to calculate noise figure, what happens when you put multiple things in series, when you have cascaded amplifiers or stages, what happens to the noise figure is something that we have seen. So now what we're going to look at in today's class, the first portion is, suppose you have your first element as some band pass filter, okay, and let's say you have your low noise amplifier, and let's say you have your mixer. Okay. Now this is a very typical receiver chain. There are of course some cellular applications where you are where you try to get rid of this band pass filter, and there are a lot of papers which have come out in what is called as solace LNAs, or basically you get rid of this band pass filter sitting in front. Now the reason why you want to get rid of this band pass filter we'll see right now. Okay. Now it is obvious, like the spectrum at the input of the antenna is quite wide. Like let's say it extends from probably 100 megahertz all the way down to okay, do any of you know how to get rid of this top bar? Okay, we'll just live with this. All right. Anyway, so here what happens is you have a very large spectrum, and this band pass filter usually is a very high Q filter, okay, which is going to kind of for example, if it is a GSM signal, and GSM band is I think roughly 880 to 920 megahertz, maybe this band pass filter will encompass some, let's say 850 to 950 or 930 megahertz, something like this. Okay, and this band pass filter will have very sharp roll off, and these are sold as separate commodities, and usually cell phone manufacturers or any other wireless communication system developer will basically, okay, you're saying try pressing Alt. Yeah, let me try that as well. Oh yeah, thanks man, thanks a lot. Okay, so basically this one is going to have a very sharp response, something like this. Okay, so this will be some high order filter, and many times it's not just some LC filters, or it's not some transmission line based filters. This will be made out of circuit, either they'll be SAW filters or BAW filters. Okay, so this SAW stands for surface acoustic wave filters, and this is some bulk acoustic wave filters and things like that. Okay, so they are extremely high Q filters. That's the point. Now these filters are typically passive devices, so they do not have any gain. Okay, typically they may have some loss. Okay, so the insertion loss, I hope you are familiar with this term, insertion loss. That is like, what is the loss of this particular element? It can be, let's say, around 0.5 dB or 0.7 dB, or let's say some 1 dB, something like that. Okay, so different manufacturers, different designs will have different values. Now you have now in previous class in the afternoon, or rather in the morning, we saw that the first stage should have as high a gain as possible, and as low a noise figure as possible, right? Because in the freeze equation, the noise figure total, right, NF total is basically equal to NF1 plus NF2 minus 1 divided by the gain of the previous state plus NF2 3 minus 1 divided by available power gain 1 into available power gain 2 and so on, correct? So you want the first stage to have high gain and low noise figure, but in most of the systems, at least slightly traditional systems, you end up with the lossy element coming as your first element. So what happens when you have what happens to the noise figure for lossy element? Okay, so let's look at that. Okay, noise figure of loss element. So the way we can kind of model this and take a look at it is basically to say you have a, okay, let's just say it's a 2-port network. So this is V in, you have RS, this is your loss element, okay, and then you yeah, again I got disconnected. Let me share once again. Right. So you guys are able to see my screen?
Yes, sir.
Right. Okay. Yeah. So let's say you have some input going into this lossy circuit, and this lossy circuit is basically modeled as this. It's just a simple Thevenin model. Let's just call it as VTH, the Thevenin equivalent voltage, okay, and it has some R out, okay. This is the model of this loss element, okay. Now, assuming, so what happens is, okay, let's say that, you know, the input impedance is Rn, okay, it has a certain Rn. Let's say that Rn is equal to Rs, that is, it's properly matched. And then you have an R out, and then, you know, this is basically the model of the loss element. Now, the loss L can be written as P in divided by P out, both in terms of available power, okay. So usually we say gain is output by input. So here loss is just the inverse of that, right? So input by output. Now in terms of what we saw in the morning, we can say V in square divided by 4Rs is your available power. What is the available power? Available power is the power that is delivered to the load if the load is conjugate matched to your source, right? So for V in and Rs, if you put a load resistance of Rs, what is the power that is delivered? So basically it will be V in divided by 2 the whole square divided by Rs, okay. So now this is the available power at the input. Let's look at the available power at the output, okay. Available power at the output can be written as VTH square divided by 4 times R out, correct. Now this can be written basically as V in squared by VTH squared into R out by Rs. Now basically VTH is some function of Vn, so some scaled function of Vn, okay. So it is just some scalar function of Vn. We are not going to it. We'll just say there is a Vn and a VTH. This ratio, for example, let's say there is a loss of some K. Let's say K less than 1. VTH is K times Vn. Okay. So we'll not go into it. We'll just say there is a certain ratio. Okay. Now, what is the noise of this particular element? So we don't know how this loss element is made up of, how this band pass filter is made up of. It has some, you know, surface acoustic wave resonator or a DAW resonator, or even if it's some LC network, whatever be the circuit inside, it can be represented as a Thevenin equivalent circuit. That's all. Okay. Now with this, what we can say is it has a certain output impedance, and therefore we can say the total noise at the output, right? Here you have RL, right? So you will get 4 kT R out, which is the noise because of this element, right? into RL by RL plus R out the whole square, right? This is the noise at the output which is added by this particular element. Okay. Now what is the overall gain here? A naught. Overall voltage gain can be written as what? VTH by Vin into RL divided by RL plus R out. Correct? That's the only thing, right? So anyway, VTH will take care of all the other effects. So in this case, we just assume that it's taking care of the entire thing. Now, what is the noise figure of this? Noise figure is basically what total noise at the output divided by total noise at the divided by the gain squared and 4 kT RS. Now, if you do that, what will you get? You'll basically get 4 kT R out into RL divided by RL plus R out the whole square into the gain basically you can write it as VTH by Vin the whole square into this divided by 4 kT RS into RL plus R out divided by RL the whole square. So basically a lot of terms cancel out here and you'll get basically Vin squared by sorry, it is actually Vin by VTH, not okay. Vin squared by VTH squared into R out divided by RS, and this is nothing but what? This is nothing but your loss. Okay. So in other words, if you have a loss element at the input, or if you have any loss element anywhere down the receiver chain or anywhere down your RF chain, if you have a loss element, okay, now the loss element, basically the figure of the loss element is equal to the actual loss of your loss element. Okay. So in this example that I gave you, where let's say if the insertion loss of your band pass filter is 0.5 dB, it means that the noise figure of that is also 0.5 dB, assuming that the matching and all that is properly done. Okay, right? Now that is the thing to do, and okay, actually I just want to make one correction. Let me just say this whole part, Rn part is not there. If you include the Rn part, it becomes difficult. So the loss element is VTH, which is producing an R out, and VTH is some K times Vin. Okay, that's the whole thing. All right. Now the input impedance of the loss element, everything is captured in the ratio of VTH to Vin. That is why we get the whole thing. So Vn out is the total noise at the output. Okay. So that is how we get the noise figure. So if you have any loss element, the noise figure of that particular block is equal to the loss. Okay. So now let's take the example of, let's say you have, let's calculate it. So please pull up your calculator. Okay, put calculators and other things. Okay, let's say this is an antenna. You have a band pass filter, and then you have an LNA. Okay, let's say this is B out. All right. Now, first an expression for the NF total. Okay, let's say the loss of the band pass filter, take it as L underscore BPF. Okay, and let's say that is some 1.5 dB, and let's say the noise figure of the LNA is taken as 2 dB. All right. So first give an expression for what is the total noise figure, and then you compute it in terms of dB, how much you will get it. So try to work it out. I'll give you a couple of minutes. You can quickly try to just use the freeze formula, and you'll be able to find it.
Sir, can you show previous slide once again?
Yeah. So noise figure of any loss element is equal to the loss value. So if you apply what is the freeze formula? It is NF1 plus NF2 minus 1 divided by gain of the first stage, right? So what is NF1 here? It is basically LBPF, right? Plus what is the noise figure here? It is NF of the LNA minus 1 divided by the gain of the previous stage. So what is the gain of the bandpass filter?
1.
No. I mean, it has a loss, no? So how will you write the gain then? Loss and gain are inversely related, right?
Okay.
So if you say it has a loss of 0.5, it means it has a gain. I mean, it has a loss of, let's say, 2. It means it has a gain of 0.5. Correct? Because it's P out by P in for gain and P in by P out for gain, for loss. So it is nothing but 1 by LBPF. So this can be written as LBPF plus NF, NF of LNA minus 1 into the loss of BPF. So this minus 1 and this 1 will get cancelled. So you will basically get NF LNA multiplied by loss of BPF. Okay. So in dB what happens? NF total in dB can be written as NF LNA in dB plus loss BPF in dB. So how much will you get? Come on guys, I've given you the value. So what will be the total noise figure?
3.5.
It's basically 3.5 dB. Okay. So what you can see here is, because it's just sum of these two, the loss of the thing directly gets added, and because it has this, it's basically like, instead of just having your first noise figure coming directly, you're having what? The noise figure of the first two elements getting added directly, right? With no impact of gain. So which is why people always try to, which is what is very important, the first stage should not be lossy. Okay, but sometimes not practically possible, because sometimes you cannot meet the other specifications, like getting rid of out of band blockers and things like that, and you have to use bandpass filters. So you use low loss bandpass filters. Okay, so which is why there is all these SAW, BAW filters which try to give you lower loss and higher Q, and you try to use them. Okay, all right. Now let's shift gears slightly, and then we'll define what is called as sensitivity. Maybe I'll just open another page. Okay. Now in the RF world, this is a term that you'll be very often, using. Okay, you say, what is the receiver's sensitivity? If you say, okay, I have a receiver, I'm buying a receiver, the first thing people will ask is, what is its sensitivity? So what is the sensitivity? Basically, sensitivity is defined as the minimum signal, okay, that a receiver can detect with acceptable quality. That is to say, what is the minimum signal that should be at the input of your receiver so that your communication is successful? That is, you are able to communicate with an acceptable BER, bit error rate, right? That is, you can say that the communication is a success, right? Now, for example, if you look at your cell phones, like your smartphones, you can go to about phone, and look at the signal strength and so on, if it's showing minus 80 dBm, minus 85 dBm, minus 60 dBm, minus 75 dBm, and you're still able to talk to talk to somebody or use your data, it means that the receiver is able to work with such tiny signals and still have a successful communication, right? So suppose that signal power drops to minus 90. Just next time you go to an area where you have very poor tower, or where the number of bars in your tower in your mobile phone is showing less, you will see that it is coming down, 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 and then after a point your mobile phone will say, okay, there is no tower at all, okay, and it is not able to detect any signal. So basically what happens is the signal strength has gone below this sensitivity level, right, that it is not able to have any successful communication. It doesn't mean the signal strength has dropped to some absolute zero, okay. There is still some signal, probably the signal available when you have zero tower, like how you sometimes have in your classrooms in IIST, right? Basically what happens is maybe the signal strength is minus 120 dBm, minus 130 dBm or something like that. There's some small signal available, or even let's say minus 100 dBm or something, but the receiver is not able to use that to have any meaningful communication, okay. That's why it shows that you have no tower at all. So here we are going to talk about that minimum limit. So how do people arrive at that limit? Okay. So should you take your mobile all around the place and then figure out what should be the signal strength, or is there a different way to calculate? That's what we are going to see. Okay. And an easier way to, it's very easy actually. What you start with the definition of noise figure, right, which is SNR in divided by SNR out. Now for an entire receiver chain, okay, remember we are doing this for an entire receiver chain, which means that your antenna, bandpass filter, LNA, mixer, variable gain amplifier, ADC, all put together, okay, is going to have some overall noise figure. So typically if you look at any receiver product or receiver paper, they say LNA noise figure is this much, but the overall receiver noise figure is something. That means you say I have the antenna going to my entire receiver chain, and then finally you have your output signals. So you find out the SNR here and you find out the SNR here. Now this is at RF and this is at baseband, okay, down conversion, gain, staging, everything is done, and finally it's basically the entire receiver as a black box, okay. So here what do you say? You say signal power divided by PRS, which is basically the source impedance power, and SNR out, okay. So PRS, we know it is 4K TRS, or radiation resistance of your antenna, and SNR out is basically here, correct. Let's just rearrange some terms. P signal is nothing but what? PRS into noise figure into SNR out, correct. Now, as I mentioned in the morning, all these numbers are actually in terms of spot noise figure, right? What is spot noise figure? It is for a 1 hertz bandwidth at any given frequency. Now, your modulated signal will have a certain bandwidth, okay. So usually what happens is, like after your down conversion, you'll put a very tight low pass filter, or at least a first order or usually a second order low pass filter or something like that, to make sure that you are taking only your band of interest, because when your mobile is communicating with your base station, you should not be reading the data from your neighbor's phone, correct. So you should be within only your bandwidth, right. So there is a certain bandwidth. So what happens is the total signal power, this is all per hertz, okay. Now here this is nothing but PRS noise figure SNR out into bandwidth, where B is basically the bandwidth of the modulated signal, okay. Let's say this is the as the bandwidth at the RF time, okay. Now the whole thing, now this is your equation, okay. Now let's say this communication system is going to be successful if at the end of your receiver chain, you're going to have an SNR out which is greater than the SNR min. So for example, let's say a QPSK type modulation scheme. I'm just giving an example. I don't think this is the right number. I'm just giving you. Let's say it needs an SNR minimum of 10 dB. I'm just throwing numbers here. Okay. So your digital receiver, right, your communication receiver, which you study in communication system, if it has a minimum SNR of 10 dB, then it can successfully demodulate your signal and have successful communication. Usually what happens is you have what is called as the bathtub curve, right? Like you have the bit error rate versus SNR, right? Sorry, bathtub curve is for different thing, I'm sorry. You will have the bit error rate versus SNR curve. That is, as your SNR improves, your bit error rate will keep improving, right? And you kind of draw a line and say, I need a bit error rate of 10 power minus 12 or something like that. And for that, let's say the corresponding SNR is 10 dB. Okay. Now, if your SNR out if this needs to be your SNR out, what is P signal min? That is the question. Okay. What is the minimum power that should be at the receiver so that after your entire chain, you have a required SNR of whatever is needed. Okay. So P S or min, which is also called as the P sensitivity, is nothing but PRS, NF, bandwidth, and SNR min. Now the same thing in dB, it becomes P sensitivity in dBm. Okay, let's write it in dBm. It becomes PRS in dBm per hertz. PRS in dBm per hertz, because it is basically 4 kTRS. And then you have noise figure in dB, and then you have SNR min in dB, and you'll have 10 log of bandwidth. Basically, you just took 10 log of the whole thing. Okay. Now, how do basically this we know, SNR min we know, 10 log of bandwidth we can take. So what is this PRS in dBm per hertz? So what is this PRS? Basically, it is this 4 kTRS, nice. You have RS, and then basically you assume that the load RL is equal to RS. Now this RL is nothing but the input impedance of your receiver. Okay. So for maximum power transfer, you need conjugate matching, and so RL is equal to RS, or the Rin of your receiver is equal to RS. Okay. So if you have this, what is the power that is delivered to the receiver? So PRS delivered to receiver is basically, as we saw, 4 kT RS divided by 4 RS, right? The power available power that we calculated. So which is nothing but kT. Okay. Now if you take kT, if you take 10 log of kT divided by 1 milliwatt, you can calculate this. You will see that it is approximately minus 174 dBm per hertz at room temperature, 300 K. You can calculate this and you can see. Okay. So it's dBm. Okay. So which is why you get this very commonly used famous equation, sensitivity equation, is minus 174 dBm per hertz plus noise figure in dB plus 10 log of bandwidth plus SNR min. Okay. So let's throw in some numbers. Let's say the SNR min that I need is, let's say, 10 dB. Okay. Let's say the noise figure of the receiver is some, let's say it is some 8 dB. Okay. 8 dB is actually on the good side, but let's say, okay. Let's say bandwidth is, let's say it's some 4G signal. Let's say the bandwidth is 10 megahertz. Now can you tell me what is the sensitivity for the signal? Can you quickly tell me? It's just simple addition basically. So it's what, 1 minus 174 plus 8 plus 10 log of 10 megahertz. So it becomes 10 log of uh, just a minute, please. Hello? Sir, yes, sir. Yes, sir. Okay, sir. Sir, actually, if you can just guide it through. No, we can just say no need of installation. Just video installation is. Okay, sir. I will just say that video installation. I mean, video help can be given while installation. Okay, I'll just send a mail, sir. Okay, yeah, thanks. Yeah, sorry about it, guys. I had to take that. Yeah. So, did you calculate what is the sensitivity number?
Minus 86.
Minus 56, is it?
86.
Minus 86. Okay. So you have 10 log of 10 power 7, right? Sorry. Yeah, 10 power 7 plus you have 10. Okay, minus 80. So basically, what it means is, if you have a signal which is going below minus 86 dBm, this receiver cannot receive your signal. Okay, and this first three terms in this equation, right? This is what is usually called as the noise floor. Okay, that is, whether you like it or not, you are going to have that noise. Okay, and it's only above that how much SNR you need, that will become your sensitivity. Okay, this is the thermal noise, basically noise floor, along with your because of your noise figure as well as the bandwidth as well as of course the thermal noise floor. Okay, is it clear? This is what is called as sensitivity, and just keep this equation in mind. It's usually used quite often where where quick calculations need to be done. Okay, all right. Now let's move to the next topic for today, with which I will try to wind up, and that is also very closely related to it, which is called as dynamic range. Okay. Now we looked at sensitivity. What is dynamic range? So dynamic range, there are a lot of different definitions actually given, but in a very colloquial way, we say it is basically the range of power over which your receiver is operational. Okay, you can basically say that, in other words, the range of input for which your receiver operates. All right. So on the lower side, we very well know that the receiver integrated noise is what is going to determine, right? So let me just draw a graph, because a picture is worth 1,000 words. So on the lower side, what will you have? You will basically have noise. Okay, this is the noise flow. Okay, now on the higher side, what is limiting your performance?
Non-linear.
Non-linear. Okay, now how much higher? So we know very well about the bottom limit. We know that we derived the bottom limit just now, right? Sensitivity. Below that, you can't receive any signal. Forget about communication. On the higher side, how to understand? So one definition is, some people say, okay, let's look at the 1 dB compression point, and that can be, some people will define it with respect to the 1 dB compression point. So if you know the 1 dB compression point, then you can say, okay, that minus my sensitivity number is basically my dynamic range. Okay, so dynamic range in this case can be written as P1 dB minus P sensitivity. Let's say 1 dB compression point at the input is, let's say, some 5 dBm. Okay, for example. and the sensitivity is, let's say, minus 85 dBm, like how we saw in the previous example. Now in this example, the dynamic range turns out to be 90 dB. Okay, but many times people may not look at the 1 dB compression point, because like even before the 1 dB compression point, we know that the intermodulation components start coming up. Right? If you recall what we looked at, intermodulation and so on, we know that the IM components keep growing as the power increases. Right? I'll just reproduce that figure here. X-axis is P in. Let's say your actual power will go like this, P out will go like this, and your intermodulation components will go with a factor of, to the slope of 3, right? This will have a slope of 1, and this is your IM component. So even let's say your 1 dB compression point is somewhere here, okay, even if not so close by. Okay, let's say the actual thing starts going like this. Okay, now something like this. Let's say this is your 1 dB compression point. You know that even here also you're having a, let's say if you take this particular point, you have so much of IM, or rather this is the IM suppression. Okay. Now there is a way to define another dynamic range parameter, which says that I will allow my intermodulation components to grow till they become equal in their power to my noise floor. So this is another definition. So different people will come up with different definitions, but this is another definition. Okay. So if you recall our discussion with this thing, we said this is our PIIP3, right? This is our IIP3 point, right? And if you recall, I put something like delta P. So if you take any arbitrary P in, right? So if this is delta P, this distance becomes 2 times delta P, correct? We had done this in, we had kind of used this, derived this in one of the earlier classes. So this can be written as PIIP3 is equal to P in plus P out minus PIM out divided by 2. Okay, so this can be done, I mean the other equation can be rewritten like this also. Okay, so P out minus PIM out divided by 2, okay, plus PIN is equal to, right, I can write the equation like this, PIIP3 minus PIN is equal to this. So PIIP3 can be written as Pin plus P out minus PIM out divided by 2. Okay. Now, if you say, okay, P in and P out are related by a factor of gain, so you can say that this can be written as P in plus G, right? And PIM out can be written as minus PIM in plus G divided by 2, where G is the gain. Now obviously the G's will cancel and you will be left with what? 3 times PIN plus, sorry, minus PIM in divided by 2, right? So let me write it in another expression here. So P in can be written as 2 times PIIP3 plus PIM in divided by 3. Okay, this is just algebraic manipulation, nothing else is there, right? Okay. Now this is basically what this equation is telling us is, this is the input value, I mean this relates the input power to the input referred IM component power. Okay. Now one way of writing this, or this is also called as the spurious free dynamic range. Okay, so basically this is defined as where you don't have any spurious tones, okay, and this is defined as a point where this input power such that PIM in is equal to the integrated noise of the receiver. Okay, that is to say, you have the integrated noise of the receiver. You don't want your tones to come above that. Okay, you have the total integrated noise of the receiver, which is nothing but minus 174 dBm plus noise figure plus 10 log bandwidth, which is basically your total integrated noise of the receiver. You want this to be equal to PIM in, input referred intermodulation component, and that is your PIM in max. You substitute, PIM in max. Okay, so what happens is you substitute that, then what happens is basically you will get PIM in max, P in max. P in max becomes what now? 2 times PIIP3 plus this whole thing, which is nothing but minus 174 dBm plus noise figure plus 10 log bandwidth divided by 3. Okay, so this is another definition for the maximum input power. The definition is to say it is a spurious free dynamic range. That's how you define it. This is the P in max. Of course, P in min is nothing but your P sensitivity. So SFDR, the spurious free dynamic range, is given by P in max minus P sensitivity, both of which we have now derived. In other words, if you look at the spectrum, the concept of spurious free dynamic range is to say that you have the receiver integrated noise. Let's say this is your receiver integrated noise, and you want your intermodulation tones, the power in the intermodulation tones, to be equal to your total receiver integrated noise. Okay, so this can kind of be little higher, and this will correspond to a certain maximum input, right? So this, let's say this is your sensitivity. Okay, this is basically called as SFDR. Okay, so you have receiver integrated noise. You can have maybe little higher tones also. Okay, this is one definition. In mixed signal circuits, it's slightly different. You basically say that you don't have any spurious tones. That's another way to define it. This is one way to define it. Another way to define it is to say that if you have this large thing, you have some intermodulation tones. For any arbitrary thing, this is what is called as SFDR. Okay, this is another definition where you kind of make the noise power equal to the intermodulation tone power. That is one way to look at it. But in many cases, you just look at the other tones and then you say this is the dynamic range over which I don't have any spurious tones at all. Spurious free dynamic range. Okay. So with this, we conclude our discussion on nonlinearity, noise figure, sensitivity, dynamic range, and all these things. Are there any questions? Any doubts? Okay. All right. So with this, we conclude this major set of topics. In tomorrow's class, I will talk about impedance transformation. So with that, we are completing chapter 2 of this Razavi's book. There is some material on S parameters which I will not be taking, because I assume that you have already done that, and Volterra series and other things. Of course, that's kind of beyond the scope of the class. Okay. So with that, we'll conclude this. From next week onwards, we'll get into LNA design. Okay. Okay. Thanks everyone. Have a nice evening.